Somewhere over the middle of the Pacific Ocean right now, air is rising in a place it almost never rises, and sinking thousands of miles away in a place it almost never sinks, and that single shift in the atmosphere is about to rewrite the weather for 2 entire continents for the next 6 months. This is not about one storm, it's not about one heat wave, even though you've probably already felt one this summer. This is about the actual machinery behind the weather itself getting rebuilt in real time by one of the most powerful atmospheric events the modern climate record has ever measured. Today, we're going to break down exactly what that machinery is, how scientists can already see it reshaping the jet stream months in advance, and why the forecast for this coming fall and winter looks unlike almost anything in the historical data. No exaggeration, just the mechanics and the evidence. If unusual weather has touched your life this year, tell me in the comments where you are. And subscribe now if you want to keep tracking this as it develops, because this story is only getting started. Let's get into it. To understand what's actually happening right now, you have to start in a place most people never think about, several hundred meters beneath the surface of the tropical Pacific Ocean. Earlier this year, a specific kind of subsurface disturbance called a Kelvin wave, essentially a massive pulse of unusually warm water moving eastward beneath the ocean surface, began developing in response to a series of westerly wind bursts, sudden reversals of the normally steady easterly trade winds that blow across the equatorial Pacific. That Kelvin wave has been rising toward the surface throughout the summer, and as it rises, it becomes visible as exactly what meteorologists call El Niño, a warm temperature anomaly spreading across the surface of the central and eastern tropical Pacific. As of the most recent measurements, water temperatures in the primary monitoring region used to track this event are running roughly 2.1 degrees Celsius above average, a reading that puts this event ahead, at this same point in its development, of every other Super El Niño event in the modern record, including 2015, 1997, 1991, and 1982. Some computer forecast models are now suggesting this could become the single strongest El Niño event since organized record-keeping began in 1950. Peak anomalies in some of the most current ocean analysis are already showing localized readings exceeding 5 degrees Celsius above normal in parts of the core monitoring region, a genuinely extreme reading by any historical standard. Here's why that specific ocean temperature number matters so much more than it sounds like it should. Once water in that part of the Pacific crosses roughly 2 degrees Celsius above normal and holds there for several consecutive months, meteorologists classify the event as a Super El Niño, a category reserved for the most extreme tier of what is otherwise a fairly common recurring climate pattern. Super El Niños don't just warm the ocean in one spot and leave everything else unaffected. They fundamentally alter the pressure balance across the entire tropical Pacific, dropping air pressure over the central and eastern Pacific while raising it over the western Pacific and the Indian Ocean. The pressure shift drives a change in what atmospheric scientists call the Walker circulation, a massive, continuous loop of rising and sinking air that normally sits over the western Pacific and Indonesia, but during a strong El Niño, effectively relocates thousands of miles to the east. Current atmospheric data confirms exactly this shift is already underway, with strong rising air motion detected over the central and eastern Pacific and a corresponding zone of sinking air over the Indian Ocean, a textbook signature of a fully developed El Niño reorganizing the tropical atmosphere. What makes this specific event genuinely remarkable, rather than just another seasonal El Niño advisory, is how locked in and persistent that atmospheric reorganization has already become, months before the event is even projected to reach its peak. Forecast models running into the start of August show a large, essentially stationary area of rising air and low pressure sitting over the tropical Pacific, held firmly in place by the sheer strength of the underlying ocean anomaly. Meteorologists have a specific term for this kind of locked-in, unmoving atmospheric feature, an atmospheric standing wave, and its presence this early in the event's development is precisely why forecasters are already confident enough to be discussing fall and winter impacts in early August, months earlier than they'd typically have this kind of confidence in a seasonal outlook. It helps to understand exactly why scientists can speak with this much confidence about a season that hasn't even arrived yet, because seasonal forecasting has historically carried a reputation, not entirely unearned, for being far less reliable than short-term day-to-day forecasting. The reason confidence is running unusually high for this specific event comes down to the sheer size and persistence of the signal driving it. A typical weather system, a single storm or a short-lived heat wave, is inherently chaotic and difficult to predict more than a week or two in advance, because it's shaped by countless smaller atmospheric variables interacting in ways that are genuinely difficult to model precisely. An event of this magnitude in the tropical Pacific works differently. It represents such an enormous, sustained transfer of heat and pressure difference across an entire ocean basin that its downstream effects on the broader atmospheric circulation become far more predictable than any individual storm ever could be, even months in advance. That's precisely why meteorologists were already discussing winter impacts back in July, and why the forecast has only grown more detailed and more confident as additional weeks of data have continued confirming the same underlying signal rather than contradicting it. Now let's connect that Pacific Ocean mechanism to the actual weather people are experiencing on the ground, because this is where the story stops being abstract atmospheric science and starts explaining the headlines you've probably already seen this summer. Meteorologists refer to the connection between tropical Pacific conditions and weather thousands of miles away as an atmospheric bridge, or more formally, a teleconnection, and it is one of the most well-documented relationships in all of climate science. During July, pressure and temperature patterns across the United States and Canada already closely match the patterns meteorologists have documented during past strong El Niño events. The main area of low pressure over North America shifted farther west than usual, allowing a warm southerly flow of air to build underneath a ridge of high pressure stretching across the central and eastern United States and Canada, while a cooler flow settled in along the west coast. Over Europe, a strong blocking area of high pressure formed over the northern part of the continent, amplifying heat across the western half, while keeping conditions comparatively milder toward the northeast. If you were dealing with a persistent heat dome across the central United States this summer, or watched a heat dome expand across Central Europe and the Balkans pushing temperatures above 40 degrees Celsius, you were experiencing this exact atmospheric bridge in action, not an isolated, disconnected weather event. Moving into August, forecast data shows that bridge continuing to evolve rather than fading away. Early in the month, the pattern favors a ridge of high pressure building over the west central United States and Canada, driving temperatures higher across those regions, while a low pressure tendency develops over the eastern half of the country. By the middle of the month, the latest ensemble forecasts show that low pressure area sliding further east, bringing a shift toward below normal temperatures across the eastern and central United States, even as the western and northern parts of the country stay locked in a warmer pattern. Precipitation follows a similarly structured pattern, with wetter conditions expected across the eastern and northeastern United States, alongside drier conditions settling into the south-central states and southern Canada. None of this is random, day-to-day weather variability. Every piece of it traces directly back to the same underlying Pacific Ocean signal expressed through the same atmospheric bridge, shifting week by week as the standing wave over the Pacific continues to strengthen underneath it. It's also worth understanding why this same Pacific mechanism produces such different, almost mirror image effects on opposite sides of North America, because that asymmetry is central to why this pattern gets described as genuinely shocking, rather than simply a warm year or a cold year. The amplified Pacific jet stream driving this entire pattern doesn't uniformly warm or cool the continent. It fundamentally reroutes where storm energy and cold air are allowed to travel. Under normal conditions, outbreaks of cold Arctic air originating over northern Canada have a relatively direct path to plunge southward into the northern and central United States during winter months, which is exactly the kind of cold snap most of the country has grown accustomed to expecting periodically each winter. A strong enough ridge of high pressure sitting directly over Canada, the kind currently showing up consistently across this year's forecast models, effectively blocks that direct southward path, holding the coldest air locked in place farther north than usual. But that blocked cold air doesn't simply disappear. Instead, it tends to get funneled around the edges of that same ridge, frequently diving southeastward along a different track that can end up delivering cold outbreaks specifically into the southern plains, the Gulf Coast, and the mid-Atlantic. Regions that infrastructure, agriculture, and daily life are generally built around not expecting sustained winter cold. That's precisely the mechanism behind the pattern researchers are describing for this coming January and February, and it explains why a warmer than average northern winter and a colder than average southern winter can both be true forecasts, arising from exactly the same underlying atmospheric setup. Here's where the story moves from interesting seasonal detail to something that genuinely deserves the word shocking. Because not every El Niño event pushes weather in the same direction, and the specific character of this one matters enormously for what comes next. Climate scientists classify El Niño events into two broad categories based on exactly where the warmest ocean water sits: Central Pacific events and Eastern Pacific events, and recent peer-reviewed research has shown these two types can produce meaningfully different downstream effects on North American weather. A Central Pacific event tends to act like a more direct hit on the atmospheric flow, generating a strong, well-organized wave pattern that reshapes winter weather across the continent in a fairly predictable way. An Eastern Pacific event, where the warmest water sits further toward South America, interacts less efficiently with the upper-level wind patterns, which can actually produce a weaker overall ripple effect across the northern hemisphere, at least in a typical event. Based on the latest seasonal model projections for the October through December period, this year's event is classifying as an Eastern Pacific type El Niño. Under normal circumstances, that classification might suggest a somewhat muted downstream impact. but this is not a normal circumstances event. The peak anomaly across the main monitoring region is projected to exceed 4 degrees Celsius above average, pushing this specific Eastern Pacific event into what researchers classify as the extreme category, regardless of its geographic type, meaning the sheer raw strength of the anomaly is expected to override the typically weaker teleconnection pattern associated with Eastern Pacific events in general. That distinction matters because it directly shapes the forecast for the second half of this year, and it's worth walking through season by season because each stage builds directly on the one before it. As the pattern moves through fall, forecast models show the core of the warmest temperature anomalies settling over the northern half of the United States and across Canada, while a more persistent active storm track begins establishing itself across the southern half of the country, keeping temperatures there closer to normal, even as the north runs consistently warm. That developing southern storm track is being driven by an increasingly amplified Pacific jet stream, which also brings a well-defined increase in rainfall across most of the United States, particularly the south, as the stronger jet pulls in more moisture and generates more frequent low-pressure systems. Over in Europe, forecast data for the same period shows warmer than normal surface temperatures settling across much of the continent, concentrated over the central and western regions, driven by a persistent westerly and southwesterly flow pulling in warm air from the south, alongside above-normal autumn rainfall across most of the continent outside of the far north. Now, here's the part of this story that genuinely earns the description of a weather pattern that shocks people, because it fully crystallizes heading into winter. NOAA's next-generation seasonal forecasting model is projecting a distinct split-flow atmospheric pattern settling over North America for the 2026-2027 winter. And understanding exactly what that means requires walking through the mechanics one more time. A strong area of high pressure is projected to build over Canada, and that ridge is powerful enough to suppress the usual flow of deep Arctic air that would otherwise regularly plunge south into the northern United States during a typical winter. That suppression directly reduces expected seasonal snowfall potential across the northern plains, the upper Midwest, and the Great Lakes region, areas that would ordinarily be bracing for a snowy, cold winter under different circumstances. At the same time, the active storm track gets displaced dramatically southward, shifting the primary corridor for winter storms and snowfall opportunities down into the central and southern plains and parts of the interior mid-Atlantic, regions that don't typically see this level of consistent winter storm activity. The temperature side of that pattern is, if anything, even more striking. Forecast data for January shows a distinct cooling footprint establishing itself specifically across the southern plains and the Gulf Coast, sitting in direct contrast to strong, warm anomalies projected across Canada during the exact same period. An almost inverted version of what most people instinctively expect from a typical North American winter. By February, that cooling anomaly is projected to deepen and expand significantly, with a broad area of below normal temperatures eventually covering the central, southern, and eastern United States, driven by cold air intrusions that become measurably more frequent as the winter progresses. Meteorologists studying this exact dynamic describe the underlying mechanism as an atmospheric highway, a persistent, amplified Pacific jet stream corridor that simultaneously locks mild, suppressed storm track conditions in across the north, while actively directing storm energy and cold air outbreaks into the southern and eastern United States. A complete inversion of the milder, quieter winter pattern the Gulf Coast and southern plains typically experience. It's worth being direct about why this specific outcome catches so many people off guard, because El Niño has developed something of a reputation in popular understanding, as simply meaning a warmer winter overall. That reputation isn't wrong exactly, it's incomplete. A moderate El Niño winter does tend to skew generally milder and drier across large parts of the northern United States. But research comparing moderate versus extreme El Niño events has found that the transition from moderate to extreme intensity produces a dramatic amplification of the entire upper-level weather pattern, not just a stronger version of the same mild, quiet winter. The deeper Pacific trough and the more powerful Canadian ridge together form exactly the kind of atmospheric highway described above, and that amplification is precisely why super El Niño winters have historically delivered far more distinct, more extreme temperature and precipitation anomalies than the milder, more forgettable El Niño events people may remember from past years. This isn't simply El Niño as usual, turned up slightly. It's a fundamentally more aggressive version of the same underlying mechanism, and the forecast data is already showing signs of that amplified pattern taking shape as early as the fall months, well ahead of winter's traditional peak. There's also a second atmospheric signal beginning to emerge alongside this super El Niño that forecasters are now watching closely, because it has the potential to further reshape the winter outlook still forming. A separate warm ocean anomaly, developing in the Indian Ocean and known as a positive Indian Ocean dipole, has begun showing up alongside the Pacific event, And meteorologists tracking both signals together note that when a strong Indian Ocean dipole develops in tandem with a super El Nino, the combined effect on the global atmospheric circulation can be even more pronounced than either signal would produce on its own. This is precisely why forecasters are treating the coming winter forecast as a genuinely evolving situation rather than a fixed prediction locked in months in advance, updating their models on a roughly weekly basis as new data comes in from both ocean basins simultaneously. It's also worth being clear about how meteorologists distinguish this kind of large-scale ocean-driven forecasting from the day-to-day weather predictions most people are used to checking on their phones. When your local forecast app tells you there's a 70% chance of rain this Thursday, that's a short-range forecast built primarily from atmospheric conditions observed over the preceding days, and its accuracy drops off fairly quickly beyond about 10 days out. Seasonal forecasting, the kind driving everything discussed in this video, works on an entirely different foundation. Instead of trying to predict specific day-to-day weather months in advance, which genuinely isn't possible with any real precision, it predicts the probability of broader temperature and precipitation trends over an entire season based on large, slow-moving ocean signals like this super El Nino that persist and evolve gradually over many months rather than changing hour to hour. That's an important distinction because it means this forecast isn't claiming to know whether a specific city will see snow on a specific day in February. It's describing which regions are more or less likely, based on an unusually strong and well-understood physical signal, to experience above or below normal conditions across the winter season as a whole, a genuinely different and, in this specific case, unusually well-supported kind of prediction. So what should you actually take away from all of this, whether you're in North America, Europe, or simply trying to understand why weather headlines have felt unusually intense this year? First, understand that the individual storms, heat domes, and unusual temperature swings making headlines this summer are not isolated events. They are downstream expressions of one coherent, physically connected atmospheric mechanism originating in the tropical Pacific Ocean, and that mechanism is still actively strengthening as of this recording. Second, if you live anywhere across the central or southern plains, the Gulf Coast, or the interior mid-Atlantic, this winter's forecast suggests meaningfully elevated storm and cold outbreak risk compared to a typical year, a pattern worth factoring into any planning that depends on stable winter conditions in those regions. And third, if you live across the northern plains, the upper Midwest, or the Great Lakes, this pattern points toward a milder, less snowy winter than usual, which carries its own set of practical implications for water supply, agriculture, and anything else that depends on a typical winter snowpack. None of these are guarantees. Seasonal forecasting always carries genuine uncertainty, even with a signal this strong. But the underlying physical mechanism driving all of it is about as well documented and consistently reproduced across past events as anything in seasonal climate science, and it is very much still actively unfolding right now. We will keep tracking this pattern as new forecast data comes in on a weekly basis through the rest of the summer, fall, and into winter, including how that secondary Indian Ocean signal continues developing alongside the Pacific event. If this gave you a clearer picture of what's actually driving the weather this year, subscribe so you don't miss the next update. And drop a comment telling me what conditions have looked like where you live this summer. Stay curious, stay prepared, and I'll see you in the next one.